Swayam Prabha. Digital India. Educated India.
Now we look at a series of counting problems under the umbrella of balls and bins. So balls and bins problems ask, in how many ways can I throw a set of balls into a set of bins? And there are several variants of this problem depending on whether you consider the balls distinguishable from each other or not. If you're just going to look at how many balls were thrown into each bin instead of saying the blue ball and the red ball were in the bin. So that is a question of whether the balls are distinguishable. Similarly, you could ask the question with the bins being indistinguishable. The bins all look the same, so you don't differentiate between two balls being in bin 1 and one ball in bin 2 versus two balls in bin 2 and one ball in bin 1. Okay, so depending on this combination of whether you consider balls distinguishable from each other or the bins distinguishable from each other, you have four variants of this problem. And that's what we'll talk about today. And these four variants correspond to counting different objects that some of them we have seen and some we will define shortly. And further, these problems can be classified into, or can be subdivided into three variants. So one is the basic variant where there are no restrictions on how you place your balls in the bins. And another variant is when you restrict that every bin should have at least one ball. And at the other end, you have also the variant where you require that every bin can have at most one ball. So depending on this, so you have three variants of each of these four kinds of questions. So that's what we'll step through in this lecture. We start with the setting where the balls and the bins are both labeled. So there are distinct objects distinguishable from each other. So we consider the set of elements, set of balls as a set with some k different balls in it, and the set of bins as another set with n different bins in them. And throwing means throwing a ball. You can throw the ball into only one bin, and you must throw it into some bin. So what you're doing by throwing all the balls is mapping each ball into a bin. So that is a function from the set of balls to the set of bins. Okay, so that's what throwing all the balls into this given set of bins means. You are defining a function from the set of balls as a domain to the set of bins as the codomain. So counting the number of different ways in which you can throw these balls is exactly the same as asking to count the number of different functions from the set A of balls to the set B of bins. And how many such functions are there? So what is a function? Recall, you could think of a function in terms of a table like this. So A and B are, A is a finite domain, so you can simply have a table with every row, each row indexed by a different element of the domain. And the function is fully specified by filling in this column in this table. Okay, so the function is simply a string corresponding to the symbols that you see here in this column. Right, so in this example, perhaps the set B is this binary set 0 and 1, and there are 4 elements in A. So a 4-bit string specifies one function from A to B. So this set of the total number of functions simply corresponds to the total number of such strings. And this is something we have already seen. If you have an alphabet of size n, and if you have a domain or a string of length k, you're looking to build a string of length k, then the total number of such strings is n to the power k, or in this case, the size of b to the power the size of a. So that's the different number of strings, so that's the different number of functions, and that is all the ways of throwing balls into bins. Okay, so just to recap then, if k is the number of balls and n is the number of bins, where there are n distinct elements, you can simply count the number of functions from a to b as n to the power k, and that is the number of different ways you can throw the balls into the bins. This is the unrestricted version, where you can choose to throw multiple balls into the same bin, or you can leave a bin unoccupied. What about the restricted version? So suppose we require that every bin can hold at most one ball. So at most one ball in the bin variant. Well, this corresponds exactly to one-to-one functions. No element in the codomain should be used for mapping two different elements from the domain. So that's a one-to-one function. And how many one-to-one functions are there? Well, one-to-one functions correspond to, again, in terms of the string, the call in the function table, it corresponds to a permutation. So the permutation of length k built out of an alphabet of size n. And we already saw what that number is. We denote it by p and k. There's a following factorial of n for k factors, or alternately n factorial divided by n minus k factorial. Okay. How about the other variant, namely, oh, by the way, p and k, remember, is 0 when k is greater than n. You cannot throw k balls into n bins. So if each bit can hold only one ball and you have more balls than bins, right? So p and k is 0 when k is greater than n. Okay, the other interesting case to mention here is when n equals k. In this case, the number of different functions, the functions we're talking about are exactly bijections, and the number of different bijections from a to b is n factorial if a and b are both of size n, and otherwise there are no bijections. Okay, and the final variant we mentioned was the no bin empty variant. So you had to throw at least one ball into every bin. So these correspond to onto functions, and the question is how many onto functions are there? It's a little more complicated, so let's go over that in a little bit of detail. First, I want to remind you of the inclusion-exclusion principle. So remember, the size of union of two sets S and T, these are all finite sets here, can be written as S plus T minus S intersection T, the size of S intersection T. So that's the exclusion part, okay? And this was a Venn diagram corresponding to that. We are discounting elements that were counted twice. And we saw that this can be extended to more than two sets. And what we need now is an extension to n sets. So we are given n finite sets, say T1 to Tn. And we are interested in counting the size of the union of all these sets. So here is the inclusion-exclusion formula. So this is the size of the union of all the sets. This is what we would like to compute. And this can be written in terms of the size of various intersections. So J here, capital J, stands for some subset of 1 to n. Okay, so you choose some set of sets, so a collection of sets, and you take their intersection. Okay, so for instance, you could take S and R, you get an intersection here, or you could take SR and T, you get their intersection there. So in more generally, you have n sets, you can take any subset of them and take their intersection. So that is what this stands for. And we would be interested in writing the size of the union in terms of the sizes of these various intersections. And here is how you need to put them together. So you need to go over every subset of n, so every collection of some number of sets, every non-empty collection. And you need to add or subtract, so include or exclude the intersection size. So here, for instance, there are three, n equal to 3 here, and there are 8 possible subsets of these 3 sets. We are interested in non-empty subsets, so there are 7 of them, and those are the 7 that you see here. So these are all taking one set at a time. This is taking two sets at a time, and this is taking all 3 sets. So there are 7 such possible combinations, and some of them you include. You have the plus sign, so these are all you add, and these are you exclude, right? You have the minus sign. So this, whether you include or exclude, depends on the size of j. So in this case, when j equals 2, when size of j is 2, so if there are 2 sets you are taking intersection of, that you exclude. And if it is 1 or 3, if it is odd, you include. So if the size of j is odd, then j plus 1 is even, minus 1 to the power even is 1. So in that case, you include. And if j is even, then you exclude. Okay, so that is the general form of the inclusion-exclusion principle that we'll need. It has a fairly straightforward proof by induction on n. So I'm not going to write down the full proof here, but here is the key to the induction step. You want to find the size of the union of n plus 1 such sets here. You write that as a union of n sets and one more set, right? So you treat this as a single set, union another set. So this is a union of 2 sets. You can use the basic inclusion-exclusion formula here. You write it as the size of these n sets plus size of this 1 set minus the size of the intersection of these 2 sets. But the intersection of these 2 sets can be written as, so using say the distributive property of intersection over union, you can write this as the union of several sets of the form ti intersection tn plus 1. So let me give it a name, qi. So the third term here, s intersection t, corresponds to union of qi, I equal to 1 to n, where qi are of this form. And now both of these things highlighted here are a union of size of union of n elements. You can use the inductive hypothesis and expand it according to this formula. And if you look at what kind of subsets are getting used here, these are all subsets of n plus 1 which do not have n plus 1. And these 2 would be subsets of n plus 1 which would include n plus 1. So this is n plus 1 itself. And these ones have n plus 1 and something else from the expansion of this one. And since the size of j here would be different because we are adding one more set here, you would see that the sign would get flipped. So I will leave it to you as an exercise to carry out this expansion and get the formula of this form. Okay. All right. So this is the generalized form of inclusion-exclusion principle, and we will need this in counting the number of onto functions. Okay. So yeah. So that's the question. How many onto functions are there from a set of size k to a set of size n? I'm going to give it a name. I'll call it NKN because it'll show up in a couple of other places later on. It's not a very standard notation. It's just something we will use for convenience. And here is the claim that this number is actually equal to the summation here. So there's a summation I equal to 0 to n. So there are n plus 1 terms. And it looks a little bit like the inclusion-exclusion expression in that there's a -1 to the I, so it's an alternating, addition and subtraction. And but the term here is n choose I times n minus I to the power k. Okay, so let's see, can we prove this? So first, let's if you for getting a better sense of what this is saying, if you expand it for I equal to 0, this is just n choose 0 is just 1, and n minus I to the power k is n to the power k. So it's n to the power k minus something plus something and so forth. Now this n to the power k is the count of all the functions from a to b. Okay, so this counting onto functions you could think of as taking all the functions and subtracting out the number of functions which are not onto. Okay, so that's what we'll do. We'll try to count the non-onto functions. And what are non-onto functions? So any function that is not onto misses out on at least one element in its image, right? So there will be some element I that is not in the image of the function. So let me call the set of all such functions which miss out on a particular element I as T sub I. And every onto function falls into at least one of these sets. Now, an onto function might actually miss out on several elements in its image, in which case it will be part of several of these TIs. But every non-onto function will be in at least one TI, otherwise it is an onto function. Okay, so this is what we are trying to then estimate, the union of a bunch of sets, and each set is defined as the set of functions which miss out on a particular element I. So now you see where we need inclusion-exclusion, because we need the size of this union of n sets. And this was the formula from the previous slide. So the important thing I want to point out is that this is what we need in the formula. We need to find the intersection, the size of the intersection. If you took some some number of these TIs and took their intersection, TJs took their intersection, what is the size? Okay, so what is a function that falls into such an intersection? Okay, so I'm claiming, and how many are there? So I'm claiming, first of all, that there are exactly n minus t to the power k, where t is the size of j. So it doesn't depend on anything else about j. It is just the number of such tj's you're picking. If that is t, then this size of this intersection is exactly n minus t to the power k. So why is that? So what are the functions in this intersection? To fall into this intersection means, say that set capital J is I1 to IT. So F is in TI1 and is in TI2 and is in TIT. So if it's in TI1 means its image does not contain I1. And similarly, its image doesn't contain I2, doesn't contain IT. So its image doesn't contain any of this I1 to IT, or the image is a subset of, the set N, which is B, difference these I1 to IT. Okay, and conversely, of course, if I give you a function whose image doesn't involve any of these I1 to IT, then it is part of every one of these TI1 to TIT. So it would be in this intersection. So this a function falls into this intersection, or the set of functions that fall into this intersection is exactly the set of functions whose image is in the set. This is a set of size n minus t. So we are talking about all functions from A to B, but only those whose images sit inside this particular set of size n minus t. So we are, that's exactly the number of functions from A to this subset of B of size n minus t. And how many such functions are there? So that's the number of functions from A to a codomain of size n minus t. Okay, so that is n minus t to the power k, right? So this is just counting the total number of functions from a set of size k, namely A, to a codomain of size n minus t, namely excluding I1 to IT. Okay, so that's the size of this intersection. Now, to complete this formula here, I also need, for the same size t, there will be many, many j's that will show up, right? Many, many capital J's. And all of them will show up with the same, coefficient here, +1 or -1, and the same number here, right? N minus t to the power k. So I can club them all together and find out how many of them there are, and multiply this -1 to the t and minus t to the k by that number, by the number of such j's. How many j's are there? There are exactly n choose t such j's, right? These are all the subsets of n which have t elements. So there are n choose t such j's. So now I do have the thing I wanted, the total number of non-onto functions. I can write as a summation. So it's a summation, overall t, but t starting from 1 all the way to n, and -1 to the t plus 1 times n minus t to the k, and each of those multiplied by n choose t. Okay, so this is the total number of non-onto functions, and I subtract that from n to the power k, and that's the final expression I need. So there's a minus here, so that changes as -1 to the t plus 1 to just -1 to the t. So that's the expression here. This is for t equal to 1 to n. I have t equal to 0 to n here to also account for this n to the power k. As we saw, this expression for t equal to 0 is indeed n to the power k. So this is the expression we wanted to show. Okay, so that's it's not a closed form formula, but it's a pretty explicit expression for nkn that you can use. This is counting the number of onto functions. Okay, so to summarize, what we discussed so far is a case of labeled balls thrown into labeled bins, and the total number of ways in which you can do that for the 3 different cases. In the unrestricted case, it is all functions from the domain of balls to the codomain of bins. That's n to the power k. If you require the every bin to have at most 1 ball, that corresponds to 1-to-1 function. So the count there is p and k, the number of permutations of length k over size n alphabet. And finally, we counted the number of onto functions, which corresponds to the case where every bin has some ball in it. So no bin is empty case. Next, we move to the case of label bins and unlabeled balls. So we're throwing unlabeled balls means we don't really care about which ball, we don't distinguish between a setting in which, say, the blue and green balls went into the first bin versus, say, the blue and red balls went into the first bin. It's just that two balls went into the first bin, right? That's all we care about. So when we say we are considering unlabeled balls, what we mean is we only care about the count of how many balls are there in each bin. We don't care which balls, okay? So that means throwing essentially corresponds to assigning counts to each bin, saying there's a number of balls that fell into this bin. The bins are distinguishable. There are n distinguishable bins, but for each bin, you just want to assign a number, saying there's a number of balls that fell into that bin. And the question is how many different ways there are to assign this number. Now, there is an important restriction on these numbers, namely these numbers across all the bins should add up to the total number of balls you have. So the numbers should add up to k. Okay. So it turns out a very nice way to look at this problem is using the language of multisets. So let me quickly define what a multiset is. Multiset is like a set, but allows elements to occur multiple times. Okay, so each element can occur in a set. If each element either occurs in the set or doesn't occur. In a multiset, it may not occur, or it can occur once, twice, or any number of times. So you need to specify how many times an element occurs in a multiset. Okay. It's only the multiplicity that matters. The order doesn't matter. So I'm using the square brackets here to denote the multiset. So there's a multiset consisting of two A's and a B. And it doesn't matter whether I write it as AAB or ABA. It's just two A's and a B. Formally, you could specify a multiset as a function, assigning counts to or multiplicities to each element in the set. So in the multiset, so for each element in the ground set, so I'll call this here the A, B. They all come from a ground set. So if my ground set is for each element in the ground set, I assign a number saying there are these many copies of that element in my multi-set. So in this example here, AAB, the multiplicity of A would be 2, and multiplicity of B is 1, and multiplicity of every other element is 0. Okay, so that's what a multi-set is, fully specified by this multiplicity function. Of a multi-set is just like in the case of what you would think of naturally. So the size of this multi-set is 3. Okay, so in terms of the multiplicity function, it is the sum of all the multiplicities. And going back to our question of what does it mean to throw k unlabeled balls into n, it corresponds to making a multi-set of size k, where the elements are where the ground set consists of the bins. So there are n bins, and for each bin you assign a count. That is a multiplicity function, and the counts should all add up to k. Okay, so you're throwing balls into bins, you could think of it as if you're taking multiple copies of the bins, one for each ball that fell into it, and finally all these bins should, all these copies of bins should add up to k copies of these bins. Okay,